So far we have discussed the definition of the Laplace transformation, its properties, and also the method of finding out the inverse Laplace transformation. You would have noticed that many of the properties of Laplace transform parallel to those that we have already studied under the Fourier transform method. And we also notice that for certain functions the Laplace transformation and Fourier transform are quite related to each other, in the sense that if you substitute j omega for s, you get the Fourier transform from the Laplace transform. For example, you have e to the power of minus alpha t ut. The Fourier transform is 1 over j omega plus alpha. The Laplace transformation is 1 over s plus alpha. So by substituting j omega for s, you get the Fourier transform from the Laplace transformation. On the other hand, suppose you have u of t itself. The Fourier transform of this is 1 over j omega plus pi delta omega. On the other hand, the Laplace transformation is 1 over s. So here there is a discrepancy. So one would like to know under what conditions will be the Fourier transform obtained by mere substitution of j omega for s from the Laplace transformation, and under what cases will they differ. This substitution will not yield us the appropriate Fourier transform. This is the question which we would like to address. Let us consider three cases. A, in the Laplace transformation, the abscess of convergence is less than 0. Now before this, it must be clearly mentioned that whenever we compare the Laplace transform and the Fourier transform, we can do it only for the causal time functions, because the Fourier transform integrates from minus infinity to plus infinity in the time axis. So f of t has values for t less than 0. There is no reason for the Laplace transform and Fourier transform to be related to each other. So whatever comparison we can make can be done only for causal time functions. So the first case corresponds to a situation where the abscess of convergence is less than 0, which means that FL of S has all poles in the left half plane. Examples: e power minus alpha t ut has the Laplace transform 1 over s plus alpha. Example A. B, e power minus alpha t cos omega naught t will have the Laplace transform s plus alpha over s plus alpha whole squared plus omega naught squared. That means here all the poles will be in the left half plane. In all these cases, we have this: the Fourier transform f of j omega is obtained from the Laplace transform of the corresponding function with the substitution s is equal to j omega. So we have the Fourier transform can be obtained from the Laplace transform by the mere substitution of s by j omega. Conversely, the Laplace transform is obtained from the Fourier transform by substituting s for j omega. So when the abscess of convergence is less than 0, Fourier transform and Laplace transform are very closely related. One is obtained from the other by substitution of s for j omega or j omega for s. Suppose I have the abscess of convergence to be greater than 0. That means there are some poles in the Laplace transformation of FL of S in the right half plane. So maybe you are having some poles here. So that means that's why the abscess of convergence is a positive number. Example of such situation will be e to the power of 2t ut will have the Laplace transform 1 over s minus 2. Now all we can say is, for such functions Fourier transform does not exist because the integral does not converge. You have f of t e to the power of minus j omega t dt. That integral cannot converge because you have an exponentially increasing time function. In such cases, Fourier transform does not exist. So there is no way in which we can relate the Laplace transform and Fourier transform. Simply Fourier transform does not exist for such functions. The third case will be when the absorb convergence is equal to 0. That means there are poles of FL of S in the left half plane and on j omega axis. On j omega axis. The absorb convergence is 0 because you have poles on the imaginary axis as well. Example, ut 1 over s cos omega naught t s over s squared plus omega naught squared. So all these are cases where you have poles on the imaginary axis. What do we do in such cases? The general rule is FL of s in general will have FA of s which has got all poles inside right half plane, inside left half plane, plus some poles which are on the imaginary axis. Let us say bk over s minus j omega k. So it will have bk over s minus j omega k, where k, the summation is on k. That means the Laplace transform FL of s can be thought of as the combination of the terms which correspond to poles on the imaginary axis plus terms which do not involve poles on the imaginary axis, which have all poles inside the left half plane corresponding to case A. In such situation, it can be easily visualized that the Fourier transform of this will turn out to be, by substituting j omega for this, FL j omega, FLS s is equal to j omega, plus corresponding to each one of these poles on the imaginary axis, you have got bk pi delta omega minus omega k. bk pi bk delta omega minus omega k summed on k. So it turns out that in such situations, for every pole on the imaginary axis and the corresponding residue, you have an extra delta function, and that is why when you go to u of t 1 over j omega pi delta omega, you are getting the corresponding residue here is 1, so pi delta omega you are getting. So this is what it will be. So to summarize then, whenever you have the absorb convergence less than 0, then the Laplace transform and Fourier transform are very closely related. Substitution s equal j omega will get one, you can require one from the other. But if you have poles on the imaginary axis, you have delta functions in the Fourier transform, you don't have delta functions in the Laplace transformation. We will close this discussion of the properties of Laplace transformation at this stage, and in the next lecture we will continue with the Laplace transformation in the application of Laplace transformation technique to system analysis and circuit analysis. But now I think it's an appropriate time to break at this point and look at an exercise on the topics that we have already discussed relative to Laplace transformation.